video, the definition and examples of a basis, the process of extracting a basis from finite subset spanning a vector space, the definition of finite dimensional vector spaces are all discussed. So, if you consider V1 etc. Vn to be members of capital V, which is a vector space, then we can have V1 etc. Vn to be either linearly independent or some Vk is a linear combination of the preceding vectors. That is, given a vector space V, and if we randomly take a set of say n vectors, what we can say about them, either they could be linearly independent or some Vk in this is a linear combination of its preceding vectors. So that is what is proved in this theorem. If V1, V2 and so on Vn are in V, then either they are linearly independent or some Vk is a linear combination of the preceding ones, namely V1, V2 and so on Vk minus 1. So if V1, V2 and so on are linearly independent, there is nothing to prove. Suppose they are linearly dependent. That is, we don't have the scalars all of them to be 0, but yet the linear combination is 0. So if we have V1 etc. Vn to be linearly dependent, then this is what we have. Now let k be the largest integer for which alpha k is non-zero. So what is the meaning of this? Now suppose I have n to be say 10. That means we have V1 to V10 to be linearly dependent, say. And among alpha 1 etc. alpha 10, the scalars, we do not know. See, we have said that there exist scalars, not all zeros. So who are all zeros? We do not know. Suppose I have say my alpha 2, alpha 5, alpha 8 are zeros. Then and of course the rest are non-zero. Then what we can do? We can rearrange the terms. So accepting these three from alpha 1 to alpha 10, the rest of the 7 members, 7 scalars will be there. So what we are going to do? We are going to rearrange and rename the terms so that we get alpha 1 to alpha 7. That without loss of generality, the same names, the same scalars, the name can be used so that alpha 7 we have, So 7 is the largest integer for which alpha 7 is not equal to 0. So that is the meaning of saying that let k be the largest integer for which alpha k is not equal to 0. Now since alpha I is 0 for I greater than k, alpha 1 v1 plus and so on alpha k vk will be 0. The rest are not there. Now vk we can rewrite from this, taking the rest of the terms to the other side, and alpha k is not equal to 0. We can multiply both sides by our alpha k inverse. So we get this, and from here we have this step, and this is vk. This is only for convenience sake that we are renaming them as lambda 1, lambda 2 and so on lambda k minus 1. So vk is lambda 1 v1 plus lambda 2 v2 and so on lambda k minus 1 vk minus 1, where lambda I stands for minus alpha I inverse alpha I minus 1, I ranging from it should be 2 to k minus 1, so that we'll have alpha 1 here and so on. So thus vk is a linear combination of its preceding vectors. So the proof of this theorem is very simple, but this theorem has 3 corollaries. We'll see them one by one. The first one says that if v1, v2 and so on vn in V have w as linear span, and if v1, v2 and so on vk are linearly independent, that is, the first k vectors are linearly independent, then we can find a subset of these vectors of the form v1, v2, vk we are retaining as such. For the remaining, we name them as v suffix i1, v suffix i2 and so on v suffix ir, consisting of linearly independent elements whose linear span is also w. So the same corollary, we'll put it in this way. If S is this collection in V, and it is such that LFS equals W. We are given that the linear span of this is W, so we can write it as LFS is equal to W, and V1 etc. Vk are linearly independent. They are written as such. Then there is a subset T, so that that subcollection is named as T with these vectors already we have mentioned of S, such that this T is linearly independent and T spans W. So we'll have to find for the given one which spans W that we can have a subset such that subset is linearly independent and it spans W. Now, so this is what we have to prove. There is a subset T of S such that T is linearly independent and T spans W. Now, if we consider S to be V1 etc. Vn and LFS is equal to W, there are two possibilities. S is linearly independent or it is not. If it is linearly independent, then as any set is a subset of itself, the corollary will follow. If not, by the above theorem, some Vj is a linear combination of its preceding vectors. So Vj is written as lambda 1 V1 plus and so on lambda j minus 1 Vj minus 1. We shall name this as equation 1. Now since V1, V2 etc. Vk are linearly independent, naturally this j should be greater than k. So it's only for this place that V1 etc. Vk are linearly independent we are using. So when S is linearly independent, then it is the corollary is directly proved. If not, only we have to consider the theorem and we have got it. Okay, so we have now we are going to do, see, Vj we have obtained as the linear combination of its preceding vectors. What we are going to do now is we are going to take away that Vj from S and call the new collection to be S prime, so that this will act as a subset of the given set, and we shall check whether this will serve the purpose. So we will first claim that this one spans W, because that is what we want. We need to have a subcollection and that still spans W. If it is linearly independent, then the corollary will be over. If not, that process will be continued. That is the idea. So we will claim now that L of S prime is W. So obviously S prime is contained in S, and so L of S prime is contained in L of S, and already L of S is equal to W. Right, so L of S prime contained in W, name that as statement P. Now we will consider a small w in capital W, so that W can be written as a linear combination of V1 etc. Vn. The reason is W is spanned by S and S consists of these elements. So we have W to be written in this way. Now here we have this alpha j Vj coming somewhere here. Right, now that is going to be replaced by, because we know that by equation 1 that Vj is the linear combination of its preceding vectors, so we'll have to replace this Vj by these this expression. So this is what we have. Now what we will do, we will collect the terms containing V1, V2 and so on, Vj minus 1. There will not be Vj term because that is only replaced by this expression. So we have this. So this is a linear combination of V1 to Vj minus 1. Vj will not be there, and Vj plus 1 to Vn. Such elements are present in S prime because S prime is S. From that Vj is taken out. So obviously our W now is a member of L of S prime. So W is contained in, small w is a member of this, so W is contained in L of S prime. If this statement is named as Q, then from P and Q we conclude that L of S prime is equal to W. That is, S prime spans W. If S prime is linearly independent, as we argued earlier, if S prime is linearly independent, then the corollary follows. If not, continuing this weeding out process, this is the word that is used in Herstein, that continuing this weeding out process, we arrive at a subset, say T, consisting of these vectors of S, whose linear span is till, it is still, that is the same T will still span W, and that is L of T is equal to W, but in which none of the elements can be written as a linear combination of the preceding ones. So the theorem what we had before this corollary was this, that is, given a set of vectors, either they are linearly independent or some weak is a linear combination of its preceding vectors. So if you are not able to write any of the vectors as the linear combination of its preceding vectors, then there is no other goal. You'll have to have them, that collection to be linearly independent. So your T must be linearly independent. Thus, if S spans W, then we can find a subset of S which is linearly independent and it spans W. So that proves the corollary. Now corollary 2 says this: if V is a finite dimensional vector space, then it contains a set V1, V2 and so on Vn of linearly independent elements whose linear span is V. Now since V is finite dimensional, it is the linear span of a finite number of elements, say U1 etc. Um. Now by corollary 1, we can find a subset of these denoted by, say, V1 etc. Vn, consisting of linearly independent elements whose linear span must also be capital V. So we have got the corollary straight away because we have, whenever V to be finite dimensional, by the definition of finite dimensional vector space, the corollary straight away follows. Now a subset S of a vector space V is called a basis of V if S consists of linearly independent elements, that is, any finite number of elements in S is linearly independent, and V equals L of S, that is, S spans V and S is linearly independent. In this terminology, we can rephrase corollary 1 as, from a set of vectors spanning V, a basis can be extracted. We can extract a basis. Extraction means we can find a subset which will be a basis because that will span and that is linearly independent. So by the definition of basis, it will be a basis. So corollary 1 says that we can extract a basis. And we can rephrase your corollary 2 in this way: if V is a finite dimensional vector space and if U1 etc. Um span V, then some subset of U1 etc. Um forms a basis of V. So it is again the same wordings, but because of the definition, it's rephrased in this way. It becomes a basis of capital V. Now we have the dimension of V. Let V be a finite dimensional vector space over a field F. The number of elements in any basis of V is called the dimension of V and it is denoted by dim V. So even though we write it as dim V, we will be reading it out as dimension of V only. So let V be a finite dimensional vector space over a field F, the number of elements in any basis. So basis means it should be linearly independent, that collection should be linearly independent, and it should span V. And these two together, if we have for a set in capital V, then we call that to be a basis. So here we have few examples for the standard basis in certain vector spaces. If we consider R3, then already we are familiar with this E1, E2, E3. E1 is the ordered triplet 1, 0, 0 and this one 0, 1, 0. This is 0, 0, 1. So that is the standard basis of V over R. So dimension of V in this case, because the number of elements being 3, it is 3. Now if we consider the set of complex numbers, in fact that's a vector space over R and over itself also. So over its subfield R, we will see what is the dimension. Now 1i, this collection is the standard basis for this because it spans, and these are linearly independent also, because once you have alpha into 1 plus beta into I equated to 0, you have the right side 0 being rewritten as 0 plus I into 0, equating the real and imaginary parts. We will get alpha to be 0 and beta to be 0. So 1 and I, this collection is linearly independent, and obviously it spans C. So we have dimension of V to be 2. But now if you regard this as a vector space over itself, then for any element, that itself will be a basis. So we have the basis consisting of only one element, therefore dimension of V is 1. Now in the case of this is the generalization of this first one. So E1, E2, etc. En already mentioned in the previous videos. So this forms a basis, standard basis of V over F, and the number of elements being n, we have dimension of V to be n. Now in the case of the vector space of all polynomial space, we call it as the set of all polynomials of degree less than n over F, then this collection 1, x, x square and so on, x power n minus 1, this set will be the standard basis of V over F, and they are n in number, so dimension of V is n. Next, the collection of all 2 by 2 matrices. So we know that this is also a vector space over F. Then these are the basis elements. They are 4 in number, and therefore dimension of V is 4. And if we consider C cross C, okay, then in that case we have the ordered pair 1 0 I 0 0 1 0 I. They form a basis over R, and so the way how it has to be written, that A plus IB, C plus ID, that's given here. So these are the basis elements, so they are 4 in number, and therefore dimension of V is 4. Now when we consider this as a vector space over C, then in that case dimension of this is just 2. Okay, so which one will act as a basis? 1 0 0 1 will act as the basis. So in that case dimension of V is 2, and here any A plus IB, C plus ID is written on this way, linear combination of these two vectors. So we have this. Now if V is just singleton 0, then dimension of V is 0. You don't have any basis, because 0 vector, we know pretty well that it is linearly dependent and not linearly independent. So you don't have a basis, so dimension of V in this case is just 0. Now if you consider Z3 square, what is Z3? It is the collection of all congruence classes modulo 3. It's consisting of the element 0, 1, 2, each one is a congruence class modulo 3. So we have in this case V to be finite dimensional vector space over F, and the dimension of this is 2, as this is a basis of V. Okay, Z3 cross Z3, either you call it as Z3 or Z3, many will call it as Z3. So Z3 cross Z3. Okay, so that collection has this as a basis, 2 in number, so dimension of this is 2. So if dimension of V is n, then any set of n plus 1 vectors in V is linearly dependent. If dimension of V is n, then any set of n plus 1 vectors in V is linearly dependent. So if you are having, say in R3, you are given 4 vectors, say, and if you are asked to check whether it forms a basis, we can make use of this remark and conclude that those 4 vectors in R3 must be linearly dependent. So this result will be proved in the next video.